I'm working at Amazon for the last 2.5 years as a data scientist. So today, this is my paper, like Taxonomy, Agnostic and Recommendation System for Procurement Classification. So here I collaborate with Dinesh Jain, he is also an FI scientist, and we have another co-partner, actually a partner. So, okay. So from the starting of this presentation, so you all know that Amazon every year almost spends billions of money across several or millions of transactions. So if someone asks me, like in which sector, how much money Amazon spends every year, it's sound pretty much easy to answer. Like from the transaction description, we can say that this is a medical transaction, or this can be comes for Amazon building construction, something like that. But we got some transactions with this kind of descriptions. So from these descriptions, it's pretty challenging for a human to understand what is the exact meaning of this item behind this description. So what can I do? Because it's very much important for Amazon to identify or to categorize every transaction to our particular procurement class or procurement taxonomy levels. Why is it? Like to keep track of spending for each category, along with for better negotiation with the suppliers for cost optimization, and also to make the audit process smooth and avoid some future compliance issues. So to solve this problem, like we thought some regular problems, like we thought of some regular solutions. Like why not we can use a regular supervised classification method, or something we can go straight forward with LLM and ask LLM to give some recommendation. So it maybe look like a simple classification problem. So here I would like to mention that for spend classification, I am using two datasets. One is for purchase order and another one is for invoice. So whatever we are talking about, it's completely based on this dataset, right? So to solve, so this is the sample dataset. Like this kind of information we have received for PO and for invoice, and out of this information, I have to predict, or our model needs to predict a particular most suitable taxonomy level for that. So yeah, so to solve this problem, some challenges we have faced till now, and this is the most common problem that every data scientist maybe face in every problem, in real life problem. So this is, first of all, I already mentioned that the data was very much redundant, full of abbreviations. Even some item descriptions are very much Amazon theme specific. And also, we have a supplier name. So here the supplier names are coming in different formats. So from this name, we can't predict like is it really meaning to Deloitte or something else. And so now coming to the challenge 2. So the challenge 2, it comes for the taxonomy perspective. So what is the taxonomy here? So basically taxonomy is a Amazon specific procurement classification level, we can say. So here we have used two taxonomies. One is very much Amazon specific, which have around 100 of 1000 or 800 to 1000 around levels. And we have another taxonomy. It has UNSPSC global taxonomy, which is used through all over the world. It has 1.5 trillions of categories. So the format of taxonomy is coming in a hierarchical manner. So where L1 is a very much high level class, and it breaks into some L2 classes, and so on. The granular level commodity is the L4 category. And we are used to map our all transaction details to the best suitable L4 category. So what is the issue with this taxonomy? So the taxonomy is not very much static. So when we have started to find the solution of our project, we plan to use the UNSPSC, that is the global taxonomy. But after 6 months of finding the solution, our product team comes to us and they move the taxonomy toward Amazon specific taxonomy. And till now the taxonomy is continuously evolving. Like after some time of point we thought like this existing classes are not enough. So we add some more class. And even we sometimes we deleted some classes. And even one class can be split into many classes. So the taxonomy is not fixed now. And now come to the third challenge, that is the almost we have zero label or easily validated data. So we know that to train any supervised model, we need a good reliable data source. So we don't have this much data to solve this problem. So after all these challenges, we can think like how can we figure out a solution based on like addressing this kind of challenges. So we have many solutions, existing solutions in the internet, but each of them comes with their own trade-offs. Like if we go with the basics supervised classifier like random forest or neural network or XGBoost, it needs, first of all, it needs a good set of reliable samples, validated samples to train the model on the historical data, and so that it can classify the upcoming classification details. And also, as our taxonomy is continuously changing, that is the classification level is continuously changing. So it doesn't make sense that we are retrain our model every time whenever a new class will be added or it will be deleted from the taxonomy. So why not we use the LLM directly? We can use that. LLM has a very much good context on domain knowledge. But is it really feasible to pass all the 1.5 million of classes to the LLM prompt and ask LLM for given this transaction details, recommend me some top 5 or top 20 best suitable commodities? No. It will increase passing all those categories. First of all, it will increase the token size and the cost will be increased. And along with that, the LLM will start with hallucinated. Like we know, like whenever we passed a lot of data into LLM, it will definitely start at hallucinated. So now coming to the third approach, why not use an embedding based model? We know these embedding based models are very much scalable. Like it's perform very well upon millions of data, and it's quite fast also. But what the problem it faces, like whenever the input details, that is the transaction inputs, are not very much well defined, the LLM model, the embedding model usually fails. That is for the chocolate bar. For this description, from the word bar, it couldn't find that whether it's really related to some food item or it's related to some foods or something raw materials. So that's why the embedding model is recommending this kind of categories. So what can we do in that case? So we notice one thing, like LLM is very good at giving some context, but it's not at all scalable. Whereas the embedding model is scalable, but it fails when the context is not good. And also we have some supplier that I earlier mentioned. The supplier is very much useful when the item is not very much meaningful. That is, suppose the supplier is Deloitte or JPMC. So from there we can understand that it can be mapped to the commodity like any consultancy or any service like this. So why not we combine the goodness of all the three methods? So to find that solution, we invented this R2 expert method, that is a hybrid system AI. So first of all, to coming to the do expert, we need some engagements. So first of all, here rather than using just the taxonomy classes, we have generated a description, a detailed description using LLM. That is, you can see it contains that what is the use case of this commodity and what kind of items can be fitted into the commodity, and so it gives basically a detailed domain knowledge. Similarly, we prepare another enrichment database for the supplier. So here we pass the supplier name to the LLM and ask LLM to provide us a normalized supplier name along with a one line of description on the supplier and some supplier tags also. So yeah. So now coming to our two expert part. So this is the first expert I'm going to describe now. So this is a hybrid retrieval engine or hybrid retrieval system. So what is the goal of this part? Here we are optimizing the complete 1 million taxonomy into top 20 categories. Top 20 categories that is suitable for every transaction details. So here what we have done, like it is basically we have used the combination of LLM results and the similarity search. So here first of all, we believed in this case that for different diseases we have to take the different medicines. The same medicine would never work. So similarly, for different inputs, we tried different methods of retrieval. So suppose we use, so first of all we use a LLM model that check the input quality. Like if it's vague, that is we couldn't predict any item or any class from it, or it's very much clear. Like we can extract an item or a service from the item description. Along with the LLM will return us some tag, like similar to the supplier tag, we have generated some tags for the items as well. Like suppose it's the item is cupcake, then the LLM will generate some tags like it can be food, it can be dessert, or it can be cakes, or maybe some confectionery items, something like that. Along with we ask LLM to recommend a category hint, like whether it's a food category or it comes under a construction category, something like that. So now we have used the LLM generated outputs in 3 semantic paths. These paths are worked in parallel for the cost optimization. Sorry, for the latency optimization. So in the context path 1, we have used the LLM generated context, that is the LLM generated tag and the LLM generated hint. And we run the embedding model and semantic search, and we have generated semantic score for each of the classes present in the taxonomy. Similarly, in the path 2, rather than depend upon the LLM completely, we just focus on the raw input, raw item details. That is, we have used the raw item description and item name for the semantic search, and we have generated semantic scores for each of the taxonomy classes. Similarly, in part 3, we have used the supplier knowledge and we have generated score. So currently, we have three individual semantic scores. But now the question is, how can we use these 3 semantic scores? So yeah, here the item knowledge is come from. Like if the item is very much vague, that is generated by LLM. So here we are prioritizing the supplier knowledge rather than the LLM generated tags and all. So here we have given more weightage to the supplier part, that is the part 3, that is the gamma, and some weightage to the beta part also, because we find that sometimes using the raw vague input is also maybe helpful. But if the item is very much clear, then we can combine all the parts. And also these weights are, it's just for this, I'm not presenting the actual weight here. And also for the weight computation, we have done fine tuning on our real-time data, and after like on taking 2 years and 3 years of data, so we have done this cross validation to find the parameter values. So now comes to the expert 2 part. So after expert 1, after taking the weighted sum, we pick the top 20 most suitable taxonomy classes for each of the transactions. And now in expert 2, we have passed that top 20 along with the item description and the invoice description to the LLM pre-ranker and asked pre-ranker to provide us the top 5 of them. It is the most suitable, mentioning that the best, the first one should be the best class that should be related to the So here we sorry, this is the architecture. Looks very messy. Okay, so now coming to the embedding training. So why we need an embedding training? So this comes about as an improvement of our Blue architecture. We find that the accuracy of the expert 2 is completely depend upon the accuracy of expert 1. Because expert 1 is giving us the top 20, and if the ground truth doesn't even rely on this top 20, the expert 2 can never find it in top 5. So it's basically very much important to improve the the expert 1 accuracy to increase the overall accuracy. And we saw the expert 1 is basically depend upon the semantic parts. So why not improve this embedding model? So till now we have used MPNet that is available in open source. We have used MPNet so far, but we find that like LLM models, embedding models are also trained on very much generic internet data. It doesn't have any context on the LLM specific terms or LLM specific claims. I'm running out of time?
No, you have 5 minutes.
Yeah, fine. Yeah, so it's very much, it doesn't have any time answer. It doesn't have any context on LLM specific terms and so on. So why not we can train the embedding model based on the LLM data itself. So for that, I already mentioned that we are very much lack of any externally validated samples. So we can't train this model in a supervised way. So that's why we find another way why not we can train it in using a contrastive learning method. So here we basically pass the LLM model, pass the pair of cleaned and the raw input context to train the embedding model. So from here, the embedding model will learn that the raw embedding and the cleaned item embedding represents the same item. So whenever it will give a raw item, and it will generate an embedding, it can understand that it should be mapped to suppose like here from the clean version, you can understand this maybe represent to a adhesive tape or something like tape. But from the raw item, it may or might not be understand that is it really a tape or something different. So whenever a raw item will come, our chained embedding model can give some better embedding version to the noisy data, and that's how it will increase the similarity search, and it can predict like the correct embedding, the correct category classes for the raw items. So for the data training and validation, so there's some data training part. So for data evaluation, we have some 1K SNA validated PO data, and similarly for we have 1K SNA validated invoice data also. So we have generated some synthetic data out of them, covering more classes also, and we have done our evaluation based on that. And along with, we have used some LLM and some human help to validate our data. And also our a model is in production, so we are asking for whoever using our model, they can give us some feedback also, and we can share that. So this is the overall performance of our model. Like you can see the Duo Expert is outperformed almost all the models, and we have tried some baseline models. So it performs all the models for any of the data set using this 100 labels means it's Amazon specific taxonomy, and this million labels means it's even SPSC taxonomy. So you can see that why it's only 93.6%. Out of all these challenges like noisy data, evolving taxonomy, and no assimilable data. So this is the best we can do as of now. And for even SPSC, taxonomy is showing only 83.8%. And we are currently working on that. We are doing some prompt engineering for our expert group to improve that. and this is the top one, top 3 and top 5 accuracy of our words. So, as a generalization perspective, we can say like it handles like noisy data, it handles no invalidated data, and it can handle like if the taxonomy is changing or the classification class is changing. So here are some applications that can be done with this.